Hello viewers, this lecture is based on the comparison of forward and backward reaction. But before starting forward and backward reaction, we should know the concept of reversible and irreversible reaction. So basically there is a minute difference between reversible and irreversible reaction, as it has a minute difference between the spelling too. There is IR at the starting and there isn't any IR. So basically, likewise, reversible reactions are those reactions in which the reactant, just suppose that I do have a reactant A plus B, and that becomes AB. Just suppose that I do have this type of reactions. In irreversible reaction, if A and B becomes AB, it cannot again becomes A plus B. There would be a product always, it will stay in product. But in the reversible reaction, AB can somehow by some processes can again become A plus B. The best example for that is the water. Just suppose that we do have a glass of water. Okay. Now we're gonna transfer this water into a cube of this cube is a little bit weird, but this is a cube of ice. Now what we have did, we have simply make this water freeze down and becomes a state of ice or become a ice cube. Now can it again become water? Yes, it can. By some of the processes, like we can heat it up and it will again become water. This is the best example of their reversible reaction. So this is the difference between reversible and irreversible reaction. So let's start with the forward and the backward reaction, because here when the product becomes the reactant, the reactant becomes a product, there is a forward reaction, and when the the product becomes a reactant, there is a backward reaction. Let's discuss it in detail. Here you can see forward reaction and backward reaction. Must keep that in mind. These are reactions of the reversible reaction, because we do denote reversible reaction by double-headed arrow, in which one arrow shows the forward reaction and second arrow shows the backward reaction. In this condition, first thing that we should keep in our mind is that forward reaction includes the process that makes the reactant into product, but in the backward condition, the product becomes the reactant. Simple. The thing that to be noted is that whenever there is a from the left to right direction of the head, that probably means that is a forward reaction. Whenever there is a right to left arrow, just like this one, that probably means that is a backward reactions. And when these both reactions in the reversible reaction combine, we do donate, apart from donating it like this, the full head, we do donate it by the half head. We're gonna simply just keep a single thing like this, Apart from this, we do this. Simple. Second point is that whenever there is a forward reaction always occur in the high speed, and there is a backward reaction at the initial point, there it is slow. Just suppose that we do have a graph. There is a weird graph I made, but this is, just suppose that this is a graph. For instance, this is the reactant and this is the product. Basically this is the reactant and this is the product. So basically at the initial, the reactants are at the high speed or at the highest peak. Why? Because we know that before start of the reaction, we do have only the reactants, neither any product. So at this initial, there are reactant that has high concentration, like the concentration of the reactants is more than the concentration of the product, or the concentration of the product at this stage is 0 because there isn't any reaction, so why there should be a product? Let me just write it here, the P and the R, so that it becomes easier for you to identify of which I'm talking about. So at the initial stage, when it starts a reaction, it goes down, like it starts a decreasing order. But the product, when there would be a concentration within the reaction, so it will go like this. Now what has happened here? Just suppose, not suppose, this is reality. Actually, here at the initial side, the reaction of the forward was high because the reactants concentration was high. The velocity of the reactants were high to be compressed to become a product, and the products were slow. But as the product reactant increases, the concentration of the reactants becomes at a constant place. Like just suppose that I have two toffees and a person is standing in front of me do not have any of the toffee. So here let me just draw it. I have two toffees. I have given him one toffee, right? Now I have one toffee, he has one toffee. Now I have given him two toffees, right? Now I am 0. Now he has given me one toffee, then he has one toffee. Now one toffee, there is an equilibrium between. But in the reaction, there isn't any one toffee, two toffee, and becomes like here we do have the equilibrium state at the second and the fourth stair, but in the reactions we do have an equilibrium space when the velocity becomes equal. Now here you can see that the starting point is fast and its starting point is slow. So that's the minute difference, and I hope that you get it. And thank you for watching with this video.